All right, folks. Last lecture. Thank you all for coming. I really appreciate it. We're going to keep up with a little bit of review of the final exam problem set that we've been doing all week. Just going to offer up a few answers to a few questions that have come in about the final exam. Will we be provided extra paper? Yeah. The exam is kind of, the questions are pretty well spaced out. Like it goes over multiple pages. So, 2 or 3 questions a page, you've got room to work around the question. There's also a blank page kind of at the end of the questions. And if you need more blank paper, you just raise your hand, someone will bring you a sheet over. The only thing is you can't take it out, right? You can't, because then someone could write down all the questions on the, and then go out and then we couldn't use them next year. The formula sheet is going to be exactly the one that's posted on CourseLink and exactly the one you've been seeing all year. So if you're used to looking in exactly the same place for your kinematics equations, they will be in exactly the same place. Will I be provided a new bubble card if I soil the original? I don't know what soil the original even means, but I assume it means some kind of error on the original. Yeah, just be careful. Be careful with how you fill in your bubble card. I posted a thing on CourseLink about how to do that. Yeah, we'll give you another one if you messed up. It's not going to like ruin your exam if you fill your name in wrong, but you don't want to waste that time in the exam. So just, you'll be able to start a little bit before the exam starts to fill it in. It won't take you long. You'll be okay there. Can you bring a water bottle in? Absolutely. Can you bring in a bunch of other stuff? No, you can bring something to write with and possibly some backup things to write with, an eraser. You'll want a pencil for writing, and yeah, a water bottle is fine. Everything else you're going to leave, like it's not in this room, but if so, you kind of leave your bags all kind of lined up at the front here, go and sit down. When you're done, you're coming back, grab your bag, and away you go. Let's see. Will you have spare masks available if we forget ours? I don't know. I don't think so. We don't bring spare masks anywhere. I don't know why we would. Maybe the exam powers that be arrange these rooms with spare masks, but I kind of doubt it. Bring masks. If you think about it now, put an extra mask in your bag and just leave it there until after exams are done. You really don't want to not be able to get into an exam because you don't have a mask. So do your best to remember that and put an extra in and put 2 extras in case, grab a handful of disposable ones in case people forget. I don't know if we're going to have them or not, but I wouldn't bet my life on it. If I am late for the exam, is there some point at which I won't be let in? Yes, you have the first hour to arrive. After the first hour, it's kind of assumed you're just not coming, or that if you do, you're not going to have enough time to complete the thing anyway. So after 3:30, no one else gets in. Oh, and if you arrive late, I think it should be obvious you don't get extra time at the end. You get as much time up to 4:30 as you arrive for. But is there a time at the end that I'm not allowed to leave? Yes. The last 15 minutes, you're not allowed to get up and go. So up until 4:15, you can finish your exam, say I'm done, TA will come and collect it, and away you go. In the last 15 minutes, pretty much everybody finishes. And so if everyone's finishing at 4:20 and getting up and leaving, the people who are still trying to take 10 minutes to finish the exam are really distracted by that. So once 4:15 hits, everyone stays put. You're finished, you just kind of sit there and stare at the walls for a little while, and everyone finishes up. And then at 4:30, everyone goes and we collect the exams. We have a few minutes beforehand to fill in your bubble card. Yeah, a few minutes, like not 20 or anything like that. I think we'll probably let people in the room 5 or 10 minutes early. You can fill in your bubble card and get all ready, and away you go. Does anyone else have questions about the final, the structure of it, not the content of it, but the structure? 20 questions, pretty good questions, like reasonable questions, not a bunch of like crazy curveballs that are going to stress everybody out. I think it's a good exam. I think you'll find it to be fair. For my version of fair, I guess. Anyone have any questions? Any questions on lab 5 is finishing up today. Quiz 10 finished yesterday. That's it for coursework. And we've got the TA help hours have been posted for next week. My office hours on Monday and Wednesday evenings have also been posted, and I'm sure Mahar will get on and post his as soon as he can. Yeah. Practice, do this practice problem set. Make sure you know this one. Work on the self-tests and the study guide. Do that second. Once you get through those, if you can handle all of those, great. You're in good shape. If there's a study guide that you're having particular trouble with, maybe it's electricity, maybe it's circuits, whatever it is, go to the textbook and do more questions on that. You'll know by the time you do this problem set plus the self-tests where you're kind of tripping, right? Don't expect the exam questions to be harder than the hardest versions in the study guide and this thing. And generally speaking, on the easier side. I'm not going to, it's not 20 3-part questions. Most of them are one calculation or no calculations, just a conceptual question. There's a few that are, you take one idea, finish that and apply it again. But it's not an overwhelming amount of work to do. Questions, folks? Okay, great. We're going to start on number 26 here. I think that's where we finished up last class. We got a lithium nucleus. Charge of 3e, accelerating from rest to a potential difference of negative 4.6 kilovolts. What's the final kinetic energy of this lithium nucleus as it moves? Final kinetic energy. We've got an initial and a final kinetic energy. What that probably means, as kinetic energy goes up, potential energy goes down, and you know how to handle this. So if I say that the change in kinetic energy is equal to the negative change in potential energy, right? That only makes sense. That's true of anything. If you have an amount of energy contained in you as a system and you don't consider any other inputs, as you speed up, as your kinetic energy goes up, your potential energy goes down. Maybe you're sliding down the hill and your potential energy due to height goes down, or maybe you're traveling through a field and your potential energy goes down. And that's going to equal negative Q delta V, because we know that about the potential energy of a charged particle moving in a field. So for the change in kinetic energy, 1/2 mvf squared minus 1/2 mvi squared equals negative Q delta V. I'm going to rearrange this to get to delta V. And you can do that. It's just algebra. It'll take a few steps. But you get a delta V is m over 2q vi squared minus vf squared. Those ended up reversing order because we had that negative sign there. This one right here. And if you drop some numbers in, mass of the proton 1.67 times 10 to the minus 27 kilograms. We have a 2. We have the charge on the proton 1.6 times 10 to the minus 19. And we have this difference in velocities, 2 times 10 to the 5 squared minus 4 times 10 to the 5 all squared. And that will equal negative 626 volts. That's the field. I did the wrong question there. Yeah, I sure did do the wrong question there. Okay, great. I'm going to do 26 now. Sorry about that. I'm reading off my answer sheet and I solved 27. Apologies, folks. What I just did was the solution for 27, 626. That's what we get here. I'll fix it when I actually post the solutions. But yeah, okay. Well, this is the answer to 26. 26 says we've got this lithium nucleus, blah, blah, blah. Sorry about that. It's the same solution, give or take. So again, for the lithium nucleus question, not the proton question, this is 26. We've got the change in kinetic energy equals the negative change in potential energy, which equals negative Q delta V. And so we're going to say that the kinetic energy at the end minus the kinetic energy at the beginning equals negative Q delta V. And it says in 26, as you can see, accelerates from rest. So the initial kinetic energy is going to be 0, right? This term's going to go away. And so I can solve for the kinetic energy at the end equals negative times the charge of plus 3 times the charge on an electron 1.6 times 10 to the minus 19, negative 4.6 times 10 to the 3 for that field that's given. And we end up with 2.2 times 10 to the minus 15 joules. Sorry about that, folks. Final kinetic energy 2.2 times 10 to the minus 15 joules. Go for it. Indeed. Why is this 2 down here? So in the rearranging of this to this, that half becomes that 2. Yeah, it's not for a doubling the charge. The charge is right as it was. It's just that half carries a multiple of 2 that comes in there. And if you do the algebra, it won't take you long. You'll see that it comes in. All right. I think from this point onward, I'm going to solve the question that I'm working on in that question, if that's not too confusing for people. Is that cool? Great. Ah, yes. Circuits where you don't have right angles. It blows people's minds, and I know that. You need to kind of be able to interpret this, but I'm going to show you, you're used to circuits come and they split, right? And one goes up and goes neatly across like this. Boom, you can see parallel lines, and so you know it's a circuit in parallel. You are always free and in fact encouraged to redraw these circuits in a way that makes you happy, as long as you do it right. And these are not too complicated, so you can. We have a battery. We go out of the battery. As we go out of the battery, it splits. It splits 3 ways. It splits 3 ways. It goes up, it goes through 2 resistors, and it comes back down and rejoins. It goes up, it goes through 2 resistors, and it comes down and rejoins. It goes through the middle through 1 resistor and rejoins. It goes through the middle, it goes through 1 resistor and rejoins. That should probably be blue. There's nothing special about that. I just forgot to change my thing color. It goes down through 2 resistors and it rejoins. It goes down through 2 resistors and it rejoins. And if I fill these in, I've got 110, I've got 150, I've got 100, which is not special because it's red. I got 200 and I got 225. And then the circuit continues on its merry way and comes back around and rejoins with the battery. Those 2 are exactly the same. All that I've done is taken this 45-degree angle that the top and bottom wires leave with and made them 90-degree turns at the top. All I've done is add a little bit of extra wire for those corners. But that little bit of extra wire makes people feel a lot better. Do people like that better? I mean, my drawing is terrible, but are you more comfortable with it that way than that way? Is that generally the feeling? Practice that. There are examples in the text where they're at angles. Practice that redraw. I can't remember what we put on the final, but it's valid. Like this is a valid way to present a circuit. It's not different. And as long as you can do that thing where you make it the really comfortable angles that you like, you'll handle it a lot better. So I'm going to do the equivalent resistance of these 5 resistors here, and I'm going to find the overall current through the circuit in that fashion. First thing I'm going to do is say the top and bottom parallel branches are in series. There's 2 series at the top and 2 series at the bottom. I'm just going to add them like we do in series. So that circuit will look like this. Up we go into 160. Across we go through 100. Down we go through, what do we got, 425 there. So I'm saying that 110 plus 150 is 260. I'm saying there's 100 there, and I'm saying 225 plus 220, 425. And thus we complete the circuit. I've just solved the series parts there. Now I'm going to solve the parallel. I'm going to say that 1 over the equivalent resistance of the entire circuit is going to be 1 over 260 plus 1 over 100 plus 1 over 425. And I'm going to say that gives me Req of 61.7 ohms. And so then what I have is a circuit that looks like this. We have a battery, we have a one resistor that is 61.7 ohms. This thing was 15.3 volts. And by Ohm's law, we can say that the total current is going to be equal to 15.3 over 61.7. That's volts, and that's ohms. 0.248 amperes. Nothing too difficult about solving the series in parallel there. If you can handle a series in parallel, these are about as simple as it gets. But the understanding is in jumping between those two pictures. Those two pictures, nothing's even been done with math. It's just a redraw of the circuit. It will help you immensely if you get familiar enough with how circuit diagrams work to be able to do that, jump back and forth between the two. All right, I have an alpha particle. We know alpha particles. We make them by nuclear decay. I have an alpha particle, a helium nucleus, charge of +2, electron charges, mass of whatever that is, entering a uniform electric field. Initial speed of the particle is something right there, and the magnitude of the field is something else. What's the minimum speed? So let's start here. We have a field that points downward. By pointing up or down, where is the generally positive end of that field? Just point, if you know it. The field points downward. Yeah, it's up. That's something you got to kind of get to right away. We see a field pointing in one direction. The negative goes at the end that it's pointing to, the positive goes at the other end. This field points downward. I'm firing an alpha particle upward at an angle there. Which direction will the field cause it to move? Point. Give me some pointing. Yes, thank you. That's good. Positive at the top, negative at the bottom. We've got a little bit of upward velocity on this thing. The field's going to push it downward because the positive charges are up here, and we have a positive charge moving, and positive charges repel each other, or the negative charges attract. Either way to think about it is fine. Can that field affect its horizontal velocity? Not one bit. So what do we have here? I'm firing a ball of some kind at an angle in an accelerating field that only points downward. What is this? What have I created here? You've seen this before. What does it look like? Anyone want to give it a shot? Different study guide entirely. Nothing to do with electronics. It is a vector. Yep. It's a two-dimensional vector solution. Yep. It's projectile motion. That's all it is. Whether I say that the thing that's moving that is gravity straight down or an electric field straight down, and whether I call that a baseball or a particle, the movement is the same. The physics is the same. Physics doesn't care about the cause of the thing. It cares about what's affecting what else. This is going to go through a parabolic path, just like a particle, a baseball hit in gravity. So if I said, I have a baseball that's hitting gravity and does this little arc thing, and I say, where is the speed the minimum? Where would you say? At the peak, at the apex, yeah, exactly. Here, we've got this particle moving sideways, and there's no acceleration. There's no force in the horizontal direction. There's a constant horizontal. Whatever that initial horizontal motion is, the speed isn't going to change. And it goes up, and it pauses because it's changing direction. The velocity for a split second is 0, and then it starts coming down under the influence of that electric field. So right up here, the vertical velocity is momentarily 0. The horizontal velocity never changes, and we don't care how they interact because they can't interact. They're at right angles. This is vector components. So because the vertical velocity is momentarily 0, and the horizontal velocity never changes through the whole thing, that's where the velocity is the lowest. And at that point, we only have horizontal velocity. And so we can say that the minimum velocity is the horizontal velocity, which is the initial velocity times the sine of 57, which is 4.3 times 10 to the 5 meters per second times the sine of 57 equals 3.6 times 10 to the 5 meters per second. There are two reasons why people hate this question. One is that you need this ability to kind of interpret, and people like working with equations, but this interpretation of something moving under a downward pointing field being the same, whether it's gravity and a ball or electric field and a charged particle, that's understanding level physics, right? And a lot of people don't care to push right through to that level. It becomes a very simple question if that's true. And then the other problem with this question, of course, is that you never use the strength of the field. You never use the mass of the electron. You don't use these things. And there's nothing people hate worse than a number in the question that I don't use to find the answer. But it's understanding that gets you to the answer here, not jamming an equation full of numbers and hoping the right thing shakes out. Yeah. Oh, I'm saying, so what the question asks for is minimum speed. So I use logic to say that the minimum speed, so like here, let's say the speed right here. There'd be some x component to it and some y component. And I would resolve those two vectors into a third vector, and that would be my speed, right? And it would point at some angle upward. Or if it was a past the apex, it would point at some angle downward. If that y, so that y down here is this much, it gets smaller and smaller and smaller and smaller until it's 0 for just a second. All you have is that horizontal. So if there's any y, the resultant vector is longer than the horizontal, more velocity. At the apex, the only contribution to velocity is sideways. So that's got to be the minimum. And that's true whether it's a ball in gravity or a particle in a charged field. Intensity level, we've done a bunch of these now. You did a bunch of these on your quiz. We'll go through these pretty quickly. Here I'm going to say, how does the intensity level change if the intensity of the sound increases by a factor of 2? It doubles. Notice I don't say it doubles from this to this. Anywhere in that intensity spectrum, 1 times 10 to the minus 10 doubled to 2 times 10 to the minus 10, 3 times 10 to the minus 3 doubled to 6 times 10 to the minus 3. The intensity level change will be the same. That's why we use this log scale. So the first intensity level, 10 log of I1 over I0. Second intensity level, 10 log, you guessed it, over I0. And I'm saying that I2 equals 2 times I1. And so the difference in intensity levels, we've done this a bunch of times. 10 log 2I1 over I0. I say that I2 is 2I1, so beta 2 has I2 over I0, and I'm saying I2 is 2I1. Minus 10 log I1 over I0. We bring in the quotient rule. The difference between those two things is going to be 2 decibels. What did I say? Nope. 10 log 2I1 over I0 over I1 over I0. And when I divide those two things out, the I1 over I0 all cancels, and I get 10 times the log of 2 over 1. And that will just equal 3. And so the difference minus beta 1 equals 3 decibels. No matter what your initial intensity level is, if you double it, the sound level gets 3 decibels louder. By what factor would the intensity of a sound change if the intensity level changes by 20 decibels? So now we're saying what's the difference in intensity level, not in difference in intensity. Very quickly, can anyone answer that question right off the top of their head? And no, not by looking at the answer, which is sitting right there in blue. The answer is 100 times higher. Does anyone know why, just off the top of their head? There's a quick explanation for this. Anyone want to give it a try? Yeah. Exactly. Every 10 decibels increases the intensity by a factor of 10. So 20 decibels, 10 times 10, 100 times bigger. But we can get to it by just crunching the numbers, not a problem. Beta 1 equals 10 log I1 over I naught. Beta 2 equals 10 log I2 over I naught. And the difference between them, beta 2 minus beta 1 equals 20 decibels. We said that equals 10 log what we just said, I2 over I naught minus 10, blah, 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 I1 over I naught. And we use quotient rule again. And we're going to divide by 10. We're going to say 2 decibels equals the log of I2 over I1, which is what happens when we use the quotient rule and we just cancel out those I naughts. And then we're going to say that I2 over I1 is 10 to the power of 2, as was said, is 100. So I2 is 100 times louder every time you get a 20 decibel increase. Doesn't matter what the original intensity level was, doesn't matter what the final was, it's always 100 times louder. Intensity level measured from a jet, 30 meters away, 140 decibels. What's the intensity level? 300 meters. Again, we've done a bunch of these things. At 30 meters, beta is 140, nope, 140 decibels, which is 10 times the log of the intensity at that point. We'll call it 1, and I naught. And if you solve that, you can say that I1 is 100 watts per meter squared at 30 meters. And then we can do that thing where we ratioed out the intensities and ratioed out the R's. By the way, quiz 4 is done, right? Yes. A bunch of questions. There was a question on quiz 4, which you probably saw almost certainly if you did more than one attempt, where we gave a graph. And it was I versus 1 over R squared. And I had a bunch of people email me and said, hey, this is wrong. I know as R gets bigger, I goes down. Right, so this intensity should drop off, and some people were like, okay, it's a squared relationship, so 1 over R squared curve looks like that. But we were graphing it versus 1 over R squared. That was the X quantity, it was there. It wasn't versus R, it was versus 1 over R squared. And I versus 1 over R squared is just a straight positive line. You've got to look at what is actually being graphed. Here I say that I2 over I1, R1 squared over R2 squared. I2 is I1 times R1. And I put some numbers in. I get 100 in here. I put 30 squared over 300 squared here. And I get that I2 equals 120 decibels. Again, same, we've done the same question kind of 3 times now. Oh, no, I2 doesn't equal 120 decibels, blarg. Sorry. I2, in fact, equals, pardon me, 1 watt per meter squared. Then I put it back in intensity level, 10 log of 1 over 1 times 10 to the minus 12 watts per meter squared. And that will equal 120 decibels. Sorry. And that 1, just so people keep track, that 1 here became that 1 here. The traveling wave is given by some equation which I've noted right there. What's the speed of the wave? Well, this is a general expression for a wave. We know that y at x and t is going to be equal to a sine omega t minus kx. We have the angular frequency omega and the wave number k. And so we can pull out here that omega equals 1200 radians per second, and that k equals 25 per meter. That's the wave number. That's how we do the units for the wave number. You could also say radians per meter. A radian doesn't actually have a unit, so it's the same either way. And we know that omega is 2 pi times the frequency, so that the frequency we can say is 1200 over 2 pi, or 190.9 hertz. And we can also say that the wave number is 2 pi over the wavelength. So the wavelength is going to be 2 pi over 25 equals 0.251. And then finally, we can say the velocity of this thing is the frequency times the wavelength. That just rejigs that one equation that you have. We're going to say it's 190.9, 0.251, 47.9 meters per second. Just playing with what is built into a wave equation. Be it a standing wave, be it a traveling wave, you got to know what those coefficients are. And it's on your formula sheet, of course. All right, now we have 4 traveling waves described by the following equations, all distances in centimeters, all time in seconds. Which has the highest frequency? Again, y at x and t equals a sine omega t minus k x. Out of omega and k, what would you relate best to the frequency of f? Which one of those kind of relates to frequency? Just did one calculation with it. What I would say is that f equals omega over 2 pi. I want the highest frequency. I should pick the smallest or the largest omega. Yell it out if you know. Largest, right? If I want the largest version of this number, I want to pick the largest version of that number, so that the bigger one divided by 2 pi is still the biggest answer. So if I want the highest frequency, I should pick the equation that has the highest angular frequency. Here, angular frequency is 4, here it's 4, here it's 60, and here it's 20. So here, the angular frequency is 60, that's going to be the highest frequency as well. It doesn't matter what the frequency is, we didn't ask that. All we want to know is which one has the highest. We shout. We're in some kind of canyon. A few seconds later, an echo comes back to our head, and we say, how far away is the wall that caused that echo to bounce right back to us? It's a sonar question. You're bouncing something off a school of fish. It's a dolphin question. It's a bat question. Echolocation, echo, sonar. It's the same question. We're bouncing sound waves and understanding from that data what's going on. Velocity is distance over time. So the distance away is the velocity times the time. 340 meters per second times 1.85 seconds. 629 meters. And hallelujah, there in my choice of multiple choice answers is 629 meters. I happily check it off. I fill it on my bubble sheet and off I go on to the next question. Is it right? Twice the distance, right? You've recorded the time it takes for that sound wave to go to the cliff and come on back. And also in that answer sheet, by the way, 629 divided by 2, 315 meters. Just be careful. Every single one of these echolocation sonar type questions, you're always recording twice the distance away from the thing. That's the nature of them. Just remember that. Here we have 3 waves, function of time in seconds at a specific location. They're all traveling at the same speed. Which of them has the longest wavelength? Can you look at the wavelength there and tell me which has the longest wavelength? We're not graphing in X. This is in T. This is a function of time. This is not a function of the space. This isn't, that's the wave sitting right there. This is in time. The analysis of it goes like this. A has the highest frequency. Why? It has the most peaks in a certain amount of time, right? That's what frequency means. How often does a wavelength complete in a certain amount of time? How many cycles per second? And B has the lowest frequency. And if the wavelength is the velocity over the frequency, the highest frequency means the lowest wavelength. So A is the, so let's just say FA is greater than FC is greater than FB. The frequency of A is greater than the frequency of C, which is greater than the frequency of B. So that the wavelength of A is less than the wavelength of C is less than the wavelength of B. So B is the highest. It's not guaranteed that you look at it and say the length of it looks like longer, so that's what I like. We have an air column here, 2.75 meters in length. What's the frequency of the standing wave? How many wavelengths are shown there? Anyone want to give it a shot? 3/4 of a wavelength. If nothing else, folks, please be ready to look at a drawing of a wave and say exactly how many wavelengths are there. You're going to have to. And this is the basis of that whole resonance and harmonics bit. Knowing in a certain space how many wavelengths fit in there. In this case, it's 3/4 of a wavelength. And so if L equals 3/4 of a wavelength, then the wavelength is going to be 4/3 L. Nope, 4/3 L, pardon me. And if V equals F times lambda, then F is V over lambda. And we know what lambda is, we just put it in there. So if I put that in, I get 3L over, oh, sorry, 3V V over 4L. Is that right? Yes. 3V over 4L. And that is 3 times 340 over 4 times whatever the wavelength was, which was 2.75, equals 92.7 hertz. Or it's also perfectly valid to recognize this is what harmonic for a tube with one end open and one end closed? Anyone able to tell me which harmonic it is? N equals, hold up some fingers. Good, it's good. The threes are coming. I like it. Thank you. Yes, it's the third harmonic. It's the second shortest wave that can fit in there, but we know for one end open and one end closed, we're working in these silly quarter wavelengths, so that's why the N goes up 1, 3, 5, 7, 9. There's no second harmonic for a tube open at one end only. This is the N equals 3 harmonic, and you actually have the equation to talk about the N equals 3 harmonic. You can say the frequency of that is NV over 4L. So F3 is 3 times V over 4 times L. Same thing. It solves the same. In fact, this logic here is where these come from. Which harmonic is it? Hold up some fingers if you like it. I'm seeing fingers. It's good. Anyone else want to throw some up just for fun? Second harmonic. Yep. The first harmonic, if you're open at both ends, is just that kind of cross like this. This is the second harmonic. How many wavelengths do you see? Got to be able to look at the picture. Yep, one wavelength is right. Got to be able to look at the picture and know that. And this is the hard one, right? This is the one that gets people. Everyone likes a sine wave. I mean, maybe you don't like sine waves. That's your problem, not mine. But everyone recognizes a sine wave. And you can say what a half a sine wave looks like. You can say what the other half looks like. You can say kind of what 3/4 looks like. This is a cos wave. It's a sine wave shifted by a quarter wavelength, right? If we extended this thing out and we said, let's draw a line here and here, that's a wavelength there, that's a wavelength there. It's the same shape. In a tube open at both ends, you're going to get a cos waveform, not a sine waveform. And you've got to kind of recognize how many wavelengths are there all the same. One wavelength there, it's the n = 2 harmonic. And we can analyze it accordingly. L equals lambda as shown. The length of the tube contains one wavelength. And so the velocity of this thing is the frequency times the wavelength, thus is the frequency times L. And so the length of it is the velocity over the frequency, which we are given 340 over 202. And we solve 1.68 meters. A little bit of beta plus decay. So we're here now. 208 bismuth. Beta plus decays. What is formed? 208 is A, the atomic mass. Beta plus decay. How does A change? Hold up a number. Up or down? Neither. Does it change at all? A. We're looking for A now. In beta plus decay, does A change? It does not. A stays the same. The mass stays the same through beta decay. A proton changes to a neutron, or a neutron changes to a proton, depending on beta plus or minus. But the mass stays the same because we consider the mass of a proton to be the same as the mass of a neutron. A doesn't change in beta decay. So, wrong and wrong. 208 remains the same. All right, now, 83 protons in bismuth. Beta plus decay, number of protons goes up, down, or doesn't change. That's the three remaining options. In beta plus decay, the number of protons goes down. Yes. 83 goes to 82. We end up with polonium 208. Beta minus decay, the number of protons goes up. The Z number, the bottom number, goes up in beta plus decay. Beta minus decay, it goes down. That's the only wrinkle in this like nuclear equations thing. Uranium-238 undergoes alpha decay. Alpha decay is the easy one, right? Alpha decay is the only one where A changes. Changes by 4. You got a helium nucleus coming out of there, 4 and 2. Uranium-238 becomes an A of 238 goes to 234, exactly right. 92 goes to 90 is correct. 234 and 90, we have ourselves some thorium. No more to it than that. And what else have we here on this delightful little set? We've got through 40 of these things. Activity. Okay, I think that's a reasonable place to say from 41 to 45, I'll do another supplemental video and post that up there. Let's call it a day. And folks, let's call it a semester. Thank you for a marvelous amount of attention and attendance. I really appreciate it. Thanks for coming to lectures. And I'll be here if you have any questions.